is the third hour of Physics 1C for, what is this, September 1st? And we're talking about the electric field of dipole. So we've got a charge arrangement that's called a dipole. And on this picture, there's this vector here, P, okay? And that vector is basically equal to, I'm just going to tell you right now, that the vector that they've drawn here is P, is basically equal to the distance between the charges multiplied by one of the charges. It's basically equal to just Q times D. Okay? And we call this vector the electric dipole moment. It's just the charge on one of the two multiplied by the distance between the two of them. This is going to show up in our answer. And it'll also show up in your homework. So I mentioned that now. All right, let's read the problem. An electric dipole is centered at the origin with P in the direction of the plus y-axis. Again, I told you what P represents. It points from negative to positive. Derive an approximate expression for the electric field at point P, right here, on the y-axis, for which y is much larger than d. So we're specifically going to look at what the value of the electric field is when y gets really big. Okay? We'll start off by finding the electric field when y is some normal value, and then we're going to use something called the binomial expansion to kind of expand this out. Have you guys ever seen this expression before? If I have 1 plus x to the n power, that this is approximately equal to 1 plus n times x plus n times n minus 1 times x squared over 2. You guys have seen that before, right? You can get this by doing the Taylor expansion of this, or there's, it's, yeah. It specifically works when x is less than 1. The absolute value of x is between 0 and 1. So, yeah, I don't know that you might have done this in algebra. This doesn't look like something you would have done in algebra. You might be thinking of something like a plus b cubed or something like that, being equal to like a cubed plus b cubed plus, what is it? It's like 3a cubed b, et cetera, right? Something like that. This is a little different, what we're doing here. It's a little different than that. It's getting really laggy, this program is. Okay, so how do we do this? Well, as drawn in the picture here, the dipole is separated by a distance d, and the point that we're considering is on the positive y-axis, and what's drawn here are the electric field vectors for each of these. The positive electric field vector E plus points up, the negative electric field vector points towards the negative charge. And I would say that if I want to find the total field at that point, what we're going to need to do is basically just sum E plus plus E minus. So what's the value of E plus going to be? Well, point P is how far away from this? It's y, the y coordinate. This would be y from here up to here. Minus this distance here, right? Which is d over 2. Can you guys see that? So that means that our electric field at this location is going to be k times the charge q divided by that distance squared. I'm sorry, my phone's messaging me. Would you guys agree with that? Does that look like the right expression for the electric field due to the positive charge? Any questions? For the negative charge, the only thing that's going to change is that we're going to have the distance from point P to the negative charge is farther away. It's y plus d over 2, right? Because if that's y, we need to add this distance between these 2 points here, right? So this is going to be k times q. It'll be negative because it points in the opposite direction, divided by y plus d over 2 whole squared. Now, in order to continue with this problem, we're going to factor out the kq. And I'm going to rewrite what's inside the parentheses in a slightly different way. I'm going to write this as a negative exponential. Not plus, minus. All right. Okay. So, next thing we want to do. Y is much larger than D. Right? We can write that up here. Y is much larger than D. All right. Now, in this problem, if we do something similar to what we did in the last two problems, we're going to run into an issue. For example, if I simply say y is much bigger than D, therefore this thing goes to y, to the negative 2. This thing would go to the same thing, right? Because if I just say y is a lot bigger than D over 2, I would get 0 as my answer. And that is not what we want. We want to get an answer that doesn't have 0 in it. All right. So we're going to have to do some things to kind of like pull the right answer out of this. Now, we have this relationship here that tells us that we can use the fact that 1 plus x to the n is approximately equal to, we're just going to use the first two terms of this, 1 plus n times x if x is much, much less than 1. Absolute value of x, actually. Doesn't matter if it's positive or negative. If the absolute value of x, it doesn't even have to be much, much smaller than 1. It just has to be less than 1, actually, I believe. So this is a little bit overkill here. But we'll be able to get this condition. So we need to rewrite, for example, y minus d over 2 to the negative 2. We want to get it into that form right there. We want to be able to use this relationship here. So what can we do to this expression to make it fit this expression here? Okay, we could put y plus negative d over 2. That's true. What else could we do? So our x would become negative d over 2. Divide for y. Why do you say that? Why would that be a good idea to do? You want to factor out a y, right? If I factor y out of this expression, it's going to become 1 minus d over 2y. Like that. You'll have a 1. That's good. That meets one of the kind of conditions that we needed. That's good. So this is starting to look like this. And then, is d over 2y going to be less than 1? Is d over 2y going to be... Is it going to be less than 1? Yeah, because of this right here, right? Y is a lot bigger than d. D over y has to be less than 1, right? Okay, so let's finish this up then. So this is going to basically become y to the negative 2 multiplied by 1 minus d over 2y. The negative 2, the n, we just bring down in front of this. So this is going to end up becoming... We take the negative 2, we put it in front. Like that. We've now used the entire expression here. And we end up getting y to the negative 2. And then this becomes 1 plus d over y. Okay, so we've now solved for what the first of our two expressions becomes right here. And you can see that the only difference between this expression and this expression is one's negative and one's positive. So what I would argue is, let's see if you guys can follow this. I think you should be able to. The first term is going to become KQ. I just drew a Y, that was my mistake. KQ. This one becomes 1 plus d over y multiplied by that y to the negative 2 right there. minus. I would argue that the second one now is going to become 1 plus, not plus, sorry, minus 1 minus d over y. And then it's also going to have that same factor of y to the negative 2 on it. Right? The y minus d over 2 to the negative 2, we saw it became 1 plus d over y. This one is going to become 1 minus d over y. You guys have any questions? Take the 2y to the negative 2's, pull them out in front. Multiply through the negative 1 to the second term so that it becomes negative 1 plus this. And we end up getting k, q, d over y plus d over y is going to be 2 d over y. And we're going to get 2k q d over y cubed. This gives us the electric field of a dipole. Specifically on axis, and this is often referred to as the far field approximation because you're really far away from it. Another way that it's written is we said before that, and it's up there above us, but basically the dipole moment is q times d. So the way this is often written is E is equal to 2k p over y cubed. This will show up in your guys' homework on the lab manual homework. So for a dipole, the electric field looks a little bit different than the electric field of just a single point charge. Instead, what you get is 1 over y cubed. If this was a point charge, this would be, I'm not even getting the ability to do my normal stuff here. There we go. It would be 1 over, 2kp came from p is equal to qd. So I just replaced that guy right there with p. That's the only thing that I did. Took a lot less time than I thought it would. Did that make sense to you guys? Does anyone have any questions? The last two lines. So this line here you're talking about? The binomial expand. Over here? Right here. Okay, so we start off with the idea that we want to get everything into this form. Our starting point is y minus d over 2 to the negative 2. The first thing we do is we factor y out. You can check to see that if I multiply y into here, it's going to repeat and give us this right here, or reproduce this right here. Right? This becomes y to the negative 2, but we also have an expression 1 minus d over 2y also to the negative 2 power. And what we do then is we take this term, we basically just bring the exponent right down in front of this guy right here, because that's what it tells us to do. If 1 plus x to the n, you get 1 plus nx. We have 1 plus, here's our x, negative d over 2y, and there's our n, negative 2. So that's n multiplied by x, and there's the negative sign here too. And then the 2's cancel, negative negative becomes a positive, and there we go. Other questions you guys have? So on your homework, what you're going to have to do is you're going to have to find the electric field off axis. And that is a little trickier. It's a little bit trickier because you're going to have components, vanishing angles, some law of cosines, all kinds of good stuff from mathematics that you'll have to deal with if you want to find the electric field at a point off the axis. All right. Anyone have any questions? Okay, in that case, what we have next, I believe, is electric field lines. We finished with 1 out of 4 things. It turns out that this is a lot more to explain than the rest of this stuff. We could explain the rest of this stuff in a very short amount of time. We won't do it all tonight. We'll probably leave electric flux and Gauss's law for Thursday. So electric field lines. What are electric field lines? Well, we've been talking about electric fields, okay? And now we want to talk about field lines. It's something that we see. Here, I'll write the word down real quick. So we want to talk about so this is a particularly specific thing that we do in physics. It's a way to kind of understand something about electric fields. Okay. I'm gonna do some things here. Let's see what can I make one of these 0? Yeah, I can. Okay. I want to look at just one charge here, and I want you to tell me the difference between what happens when there's 1 versus 2 versus 3 versus 4 versus 5. What do you notice is happening as I increase? Okay, what I'm doing here, by the way, to be clear, red means positive. This is a positive point charge. It has a value of 3. Okay. I go down to 2. It looks like that. I go down to 1, it looks like that. What do you notice is happening as I go from 1 to 2? Much more dense in the field. That's a very good way of putting it. What in particular is more dense? What in particular is more dense? More field lines. More field lines, exactly. And that's all that I wanted you to notice from this. Notice that I believe, I don't know if how exactly this program does it, but I think if it picks at 1, I believe there's 8 lines here, right? The distance between them decreases, which is another way of saying that they're more dense, right? How many lines do you count here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it 10? Yeah, it's 10, right? There's 10, right? It does correspond to more strength, that's right. So if I double it, are there 20? I don't know if there's quite 20. 1. So we start with this one. 1. It is 20. So it doubled, right? You went from a charge of unit 1, you went to a charge of unit 2, and you doubled the number of field lines. That's what I would have expected. That's kind of the way this is often described as to how you should draw them, is that if you double the size of the charge, you need to double the number of lines coming out. Now, these lines are not electric fields, right? Electric fields have a value at a given point in space. What these lines are is what happens if you draw a straight line through the field, through the vectors. They're the tangents, yeah, exactly. It's just a line, smooth line that's drawn through all the electric field vectors. It shows up on these two. If I go back to my point charge, see, the point charge has these field lines that are all pointing out at it, or in the case of a positive charge, all pointing away from it, right? But if I change it from field vectors to just field lines, those just become straight lines, right? Where you're just connecting the lines. You don't care about this. You don't care about the lines representing anything about the field strength. But encoded within the number of lines is the field strength, as you guys said. Because if I look at a region right here, really close to the charge, I see the lines are extremely close to each other. And that fact, the fact that they're so densely packed, means the electric field must be very strong in this region, or else you wouldn't have so many lines in that region. Compare that to out here, the field lines are very spread out, right? So that's one of the things that we can say about this. I'm going to write that down on our little notes right here, is that electric field lines are tangent to the E fields. The density of the lines is proportional to the field strength. Okay. All right. Now, this is just for a single point charge. And of course, as we make it stronger, we get more lines. And that's simple enough to understand. But what happens if I have a positive point charge and a negative point charge? According to this picture, I get this picture like this. Now, where does this picture come from? Let's see if we can gain some kind of understanding of that. So suppose that I take 2 points in space on a line, and I put here a negative charge, and I place here, a little bit farther away, a positive charge, positive Q. And I ask the question, what does the electric field lines look like for this kind of arrangement? How would I figure that out? So what I would do is I would come to each point in space and I would start drawing field vectors. Okay? At this point in space, I would say, well, the positively charged object is going to produce an electric field vector that points this way. The negatively charged object is going to produce an electric field that points that way as well. So I can pretty safely say all along this line that I'm going to get an electric field line here. It's going to point from there to there. It leaves the positive charge, and it finishes or ends on a negative charge, right? What if I come up to a position that's right in between the two of them? At this location, I'm going to get electric field vectors that are going to point towards the negative charge and away from the positive charge, right? The net effect being that I'm going to get an electric field vector at this location that points to the left. What about if I come to some point, I don't know, like maybe like right here? At this location, I'm going to get an electric field for the positive charge that points way up this way, and a slightly smaller version that's going to point that way for the negative charge. And the net electric field is going to be kind of somewhere in between. All right? Now let's erase some of those vectors now that we kind of know how to do that. And let's just say that as I go from this point right here where I know that the electric field points this way, and I come back to this point here and realize that the electric point kind of points that way, as I get closer to this, it's going to tilt more and more away from this point. And as I get closer to here, it's going to tilt more and more towards the negative charge. All told, when I add those together, and you can do this for yourself, I get a smooth line that's going to basically go from there to there. And the exact same thing is going to act on the opposite side. And you'll keep getting lines like this, looping around like this. I'm not really doing a great job of this, but it's kind of hard to do. And this is going to be kind of like what your electric field's going to look like if the two charges have exactly the same sign. Eventually, some of these lines, you might not be able to draw them on the page. Maybe you start to loop around like this, and eventually the lines go off the page. That, like that, like that, like that. Oh my god, it's looking awful. It's just when you try to draw this stuff by hand, it just looks awful. But yeah, it looks a lot like a magnetic field, exactly right. Making sure that these things come in like this, they go out that way, out that way, out that way, and they come back in like this. Yeah, you get these field lines. It's just kind of, you can go crazy with this stuff. We can compare back to their picture, and we'll see that mine's horrible by comparison with theirs, but it has the same general features. And the same thing happens here. If I increase the size of these charges, like that, the field gets more dense. It starts to look a little bit more like what I drew, right? So where's the densest part of this field? It's all within this region over here. Close to the charges, it's really dense. Yeah. All right, so yeah, do you guys have any questions? That's basically what an electric field is. All right. So, what if electricity is just a moving magnetic field? I mean, kind of. Moving a magnet can produce electric fields, that's for sure. So, I don't know what to say about electric field lines. Density of the lines is proportional to the electric field strength. It's tangent to the electric field. Yeah. I said I would teach you Flux. We can talk about Flux now, I guess. I just want to mention that what I said right here is that it's something we can put into words. We could say that the number of lines per unit area, let's say, should be proportional to the electric field strength. That's something that's worth remembering for what we're going to do next. So if we want to understand what electric flux is, if we have some idea of what electric field lines are, this is what we're going to need to take from this. This is what you guys noticed from looking at that picture, right? Was the place where the lines were the most dense, right? Was the place where the field is the strongest, right? And I chose to divide by area here, and why did I do that? Well, it's because these things are three-dimensional, right? They're three-dimensional. And if I want to understand something about the density, I can't really see the density in 2 dimensions, right? I mean, I could describe, let's go back to the picture where I could describe the number of lines per unit length in this region, but that completely forgets the fact that this is something that we could rotate around this axis right here if I want to produce the actual electric field of this. And we can see it on this other diagram here. And again, you can find these things to play with them on canvas. So if I plug in here a point charge, that's the same sign. Dipole, that's what we want, right? The dipole actually has, this is the real dipole, electric field lines. And if I want to talk about the strength of these field lines, what I really need to do is to look at their density by taking an area and sticking it inside of here. Like a surface area kind of thing. And it's going to be the place where you get the number of lines divided by the surface area being the biggest. Like right here. Right here. That's the place where the electric field's the biggest. Right? So given that that's the case, we can immediately move into talking about electric flux and what it means. So suppose that we take we start from here. Oh, nope. I wanted to copy this one. I'll just cut it. Why doesn't... Okay, whatever. We'll drag it. That's fine. Starting from this idea right here, that the number of lines per unit area is proportional to electric field strength. Suppose that we wanted to construct a new vector. Not vector, scalar, my bad. And this scalar is going to be something that we're going to call electric flux. Electric flux is going to be something related to the flow or somehow related to the field lines, basically. And what we're going to do is we're going to say that this flux, in its most simple form, we define like this. We use the symbol phi, capital Phi. So phi flux is kind of how you can remember this. Phi sounds like the F in flux. The simplest version of this is simply that we're going to take an electric field and we're going to multiply by some area. Okay? We're going to take an electric field and we're going to multiply it by some area. And I'll give you some examples of how this might look. So suppose that I give you some electric fields and I say that it's this nice straight electric field. Okay, so we copy this one. I'm gonna make a nice kind of straight electric field here. We'll make it like that, and then we'll just duplicate it. So I've got this nice straight electric field. Let me shift it over so it lines up like that. Oops, didn't get all of them. So we've got this nice straight electric field. Okay. And we're going to make a uniform electric field. So our electric field in this case is just this nice straight electric field. Maybe it's equal to something like 90 newtons per coulomb. Those are the units of electric field multiplied by I hat. And I tell you that this is the x direction and that's the y direction. So we have this uniform electric field in some region of space, right? And then I say, suppose that I want to take a sheet and I want to calculate how much of this, I don't know if I can do this without drawing my own thing. I think I have to draw my own thing. We'll draw it off here to the side. So we're going to draw a square, not a square, but yeah, a square. But we're going to have it tilted. So it'll have the same length on both sides, like this. That should work fine. And then we're going to connect it between there. Copy, paste. You don't want to copy, paste that? Copy, paste. There we go. here. So suppose I want to take this sheet, and I tell you that this sheet has an area that we call A. Okay? We got this sheet, right? And what we want to do is we want to find what we call the electric flux through this sheet. Okay? And the way we're going to do that is we're going to put it inside of our field right here. Okay? And we're going to calculate kind of the flow of the electric field through that, right? And let's say that our sheet has dimensions so that this side over here is like 1 meter, and this side over here, let's say, is 3 meters or something. Okay? 1 meter by 3 meters. And I want to find the flux. Well, it's really easy to do based on this definition, right? And whether you understand what it means or not, we just do the calculation blindly. We say the flux is equal to the electric field, which is 90, times the area, which is going to be 3 meters squared, right? And that gives me an answer. 270, the unit ends up being newtons times meters squared divided by coulombs. All right, that's the flux. What does it mean? I don't know, I'll tell you in a second. That's an example of a flux calculation. That's very easy to do, okay? But now we think, I placed this area, this sheet, so that it was effectively perpendicular to the field in a way, so that the field was passing straight through it, right? I can reduce the flux by simply twisting or changing the angle of the sheet right here. So if instead I gave you a sheet, and I said that the sheet, and again, I guess I have to draw it like this. So suppose we draw our sheet like this now. So we take a sheet, but we're going to make it kind of parallel to the field. Okay. So now we take a sheet, and this sheet has some area, I don't know, different area, it doesn't really matter. And now we take our sheet and we put it into our field here, like this. So the difference being that the first sheet is oriented kind of coming with its edge coming out of the screen. This sheet is oriented also with its edge coming out of the screen, except for that edge is parallel to the field lines, okay? I would say the flux through this surface is 0. It's almost like the field lines have to actually penetrate the surface to have any flux at all. In order to have flux, the field lines have to actually penetrate the surface, and if you turn it sideways, you get no flux. Okay? Now, if you want to understand what's meant by this, instead of talking about electric flux, we can switch over to a different type of flux that I believe is much easier to understand. Okay? So, consider the following. Suppose you have a house. Yeah, it's similar to fluid flow. Yeah. Suppose you've got a house, okay? So here's your house, and you've got like a very, very simple house, but it has, on its roof, what you have are solar panels, okay? So on the roof of this house, you've got solar panels, just stacked with solar panels here. And we think about what happens as the sun goes through the sky during the day. So here's the sun up here, shining its rays everywhere, right? When the sun is at its most, at the highest point in the sky, which would occur at noon, right? The sun's rays all basically shine straight down on this object, right? And you get the maximum solar flux. So at noon, when the sun is shining straight down and the rays of the sun are basically all coming parallel because it's so far away, you get the maximum efficiency of these solar panels, right? Would you guys agree? The solar panels are going to work the best when the sun is shining the strongest. And at this moment in time, these solar panels are basically going to be powering some type of battery to store up for nighttime, right? You'd be storing up all that energy that came in the daytime, because you know at some point the sun's going to go down and you're not going to be able to use that energy anymore, right? So you better have some battery that you're powering it up with so you can watch TV at nighttime and stuff like that and wash your clothes and stuff, right? Now, when the sun comes, let's say, on the horizon, so when the sun sets, so like the sun comes and now the sun's over here, right? There's going to be a certain point when those rays of the sun are just coming in at a super shallow angle, and the intensity of the light that actually hits your solar panels is going to be really low. At that moment, we'd say the solar flux is basically 0. So you would get maximum solar flux when it's at noon, and you get 0 solar flux from when the sun sets until it comes back around and rises again, right? Yeah, intensity is power over area. That's right. So that, yeah, okay. Why does the intensity go down if there's a different angle? Well, I hope from this comparison, if you agree that you go from maximum intensity at noon to 0 intensity at nighttime, then you have to agree that somewhere in between you get something in the middle, right? So if the sun is up here, okay, and we use a different color, it has to be something in between, right? It's some value in between, because now the intensity of the light is only some fraction of it is actually going to be picked up by these solar panels, right? So that's the idea of what flux is. It says that you get maximum flux when the lines that are coming in are perpendicular to the surface, okay? You get minimum flux when the lines are parallel to the surface, like this one right here. None of the lines actually cross through it, right? And when there's an angle between the two, okay, and what does that look like? When there's an angle between the two, and this is where I want to draw like a simpler picture. Suppose that our electric field is just given by these straight lines like this. And I place within this a surface, and here's my surface, and I'm only looking at the edge of my surface now. I mean, yes, it has some dimensions to it. Okay, there's my surface, okay? But now I tell you that my surface, right, kind of points at an angle. Now, how am I going to represent this angle? Well, I'm going to say that the surface itself produces an area vector that points this way. And the black lines are going to represent the electric field vector. Now, how do I draw this area vector? Well, I draw it just like I draw the normal force in Physics 1a. I draw it perpendicular to the surface, right here. If we do that, then an angle is made right here that we call theta, and we could come up with a more proper definition of flux, which is that the electric flux for this type of situation is going to be E times A, and now we need some diminishing factor that changes as the angle changes, and that is a more general definition of what flux is. This would be the Physics 2b definition of flux. We're gonna have an even better version here in a second. But this is electric flux here. Okay. All right. Now, what is the flux then, and how do we think about it? Well, I told you above. Okay, does it make sense to you guys? You'd have this cosine theta thing. Does that make sense? We really only care about like the component, right, that's parallel to the electric field. Okay. When theta is equal to 0, you get max flux. When theta is equal to 90, like here, you get 0 flux. Now, I've said that the flux is related in this sense. The number of lines per unit area is proportional to the field strength, right? So what are we doing when we do flux? Okay. So the field strength is like the number of lines per unit area. Like, this is something your book doesn't do, and I don't know why they don't do it, because I think this is, you're right, Meowers, it's the projection, right? The projection of that area vector onto the electric field, or the electric field projection onto the air, however you want to think about it. So, flux, right? We're putting this into words now as the goal here. Flux is electric field, which we just said, density of the lines. That's what I'm writing right here. You guys said the densest regions are the place where the field's the strongest, right? So the electric field is directly proportional to the number of lines per unit area. This is super simple. We're multiplying by area, and then we're multiplying by cosine theta is just a fraction, right? So what does that tell us? Flux equals probably proportional to just number of lines. This is where the idea of electric field lines starts to become really powerful. The flux is, we're not going to say it's equal, it's proportional to. It's proportional to the number of lines that pass through the area. Right? Does that make sense? When you think of electric flux, you should think of number of lines. All right? Now, let's talk about this in a more general sense. Suppose that I give you the following two setups. I say, I take a positive charge Q, okay? And I encase the positive charge Q into a cube. Why does this thing not have cubes? I hate it. How can there only be 4 shapes on this program from Microsoft, one of the most powerful companies in the world? They've got 4 freaking shapes in this program. All right, let's make it bigger. Let's copy paste. Ooh, don't do that. All right, we're gonna encase our use a Linux. Yeah, the Linux ones are really good, Nathan. Yeah, I know, dude. They're awesome. I used to have a dual boot Linux going. Why does it do this? Why doesn't it want me to copy? Paste. There we go. Ooh, whoops. I think I can still click it there, right? I used to use Linux when I worked at a laboratory, but it's like it wants me to... Here. Copy, paste, paste. There we go. Okay. So we take our cube, which I now realize I don't know if I can even select this whole thing. I can. Okay. And we're going to put our charge, here we go, inside the cube. All right. So suppose that I now go ahead and I draw some field lines, okay? What do the field lines look for my positive charge? They're basically just lines that come out like this. They go out like this. They go out like this. Go out like this. Go out like this. Right? So if I draw 8 lines, right, then the electric flux through this cube right here is going to be something like 8, right? What happens at that point? What happens then if I double the charge here? What happens to the flux? Does that make sense? It'll increase, but more specifically, like Nathan says, it will double it, right? So if I double the charge, I have to double the flux. Now, how did you guys know that was the answer? How did you come to that? What happens to the number of lines if I double the charge? You get more lines, right? You get double the lines, yeah. So by doubling the charge, I get twice as many. I get twice as many lines, right? Let's, in order to kind of drive this point home, I wanna go to 2-dimensional drawing so I can do this a little quicker because we're kind of out of time. What if I increase the size of the cube? What if I increase the size of the cube? So what if I take my same point charge Q? How do I didn't remember picking a different charge. Okay, whatever. I take my point charge Q, and now around this, I just draw a bigger cube. Right? I draw a larger cube. Maybe I double the volume of the cube or something like that. What's going to happen to the flux now? It's the same flux, right? It's still going to be the same number of lines that are going to cross out of this area because these field lines, they go on forever. They don't care about the size of the box, right? So it's the same flux in this case, right? Same flux in both cases. The size of the shape, it doesn't actually... Not only does the size matter, it turns out that it won't even matter what type of shape I choose, right? I could choose a circle and then make that into a sphere and say, what's the flux through the sphere? It'd have to be the same. Right now, we don't have a way of immediately knowing what the answer to the question is, but we will get an answer, and it turns out it's really simple. It turns out it's directly proportional to charge, but if I choose a sphere, you're going to get the same flux through the sphere as you would through... It doesn't matter what the size is. So if I want to increase flux, I got to increase the size of the charge, right? The only way to increase the flux would be to increase the size of the charge. All right. But then the question becomes, how do I calculate flux in a situation like this? Certainly it's going to get kind of complicated, right? Because these field lines are at an angle, and this is at an angle, and this is at an angle. So I'm going to have to kind of integrate, as you guys are saying, do some kind of surface integral of some kind, okay? When I have some kind of surface like this, what I have to do is I have to say, take my point charge, okay? Take a surface, like let's say we take the surface of a sphere, for example. Ooh, that looked awful, I'm sorry. Drawing really low on the page here. So I have a sphere, right? I'm going to come to the surface of this sphere right here, and I'm going to break the entire surface of the sphere up into little pieces. Up into little tiny pieces like this. I'm going to break the whole sphere up into little tiny pieces. As if we just drew a grid over the entire sphere. And I'm going to say every one of those pieces is going to have an infinitesimal area element that we're going to call dA, pointing always away from the surface of the object. Just like that. Okay. And in order to find the flux now, what I'm going to have to do is I'm going to have to come to every single one of these points, and I'm also going to have to draw an electric field vector, like that. I come to another point over here, and I say the electric field points this way. Okay, just depending on what your surface is, right? And then what you do is you say, every single one of those pieces is going to contribute to our flux, and we're going to define that electric flux as being a surface integral. The way we write this in physics is usually by just like, what? No, I'm getting ahead of myself. You would just do a surface integral of E dot dA. That is the more sophisticated definition of flux. And I will write an S right here, and you guys can decide if you really want to write a second integral here. I'm going to say, just to piss off your math instructors, that I'm not going to do that. Not really. I know that they don't like it when I only write one, but that's it. That's our definition of what flux is. Yeah, they hate me, by the way. I've heard a lot of the teachers in the math department are just like, oh, that Murdoch guy and those people in the physics department. No, I'm not. They don't single me out. That's not true. But I do know that there's some competition in terms of like the way in which we want you guys to understand these things. And I'll tell you in physics that the way we're going to understand these surface integrals is probably going to be a little different than the way you learned them in your math classes. But the way we'll teach them will be in such a way that hopefully you'll be able to use them to solve your homework problems, and you'll be able to use them to analyze to analyze electric fields. Ultimately, what we're going to be using this for is something called Gauss's law. And I actually just told you what Gauss's law was, and you guys kind of figured it out in a way. But what we're going to prove next time is that the electric flux through a closed surface only depends on the charge that's inside. That's it. So while this looks kind of complicated, we're going to learn ways to do this integral that allow you to, well, find electric fields in really simple ways by using symmetry. And that's where we're going with this. All right, I think this is our official ending time, or at least 9:10 is. So I'm going to stop right now, and I'll take questions. Do you guys have any questions?